Hello, in this video I will tell you more about the continuous spectra. So before that, light emission. Just a quick revision. Light emission is the light that you have from any elements when you have a dark background, and you see that emission here is unique to each element. I hope you can still remember that. So that's a light emission. And also sometimes you might encounter this word band emission here. So band emission here, you can see rather than getting a line here, you might get a very it's a band, or rather say a very thick line. So why do we have that? Usually band spectra, you can find it if you have very complex elements. For example, you have molecules or even any polyatomic ions here. Because very dense molecules, you will see that there are a lot of these energy levels, so they might overlap to give you a very broad line. We call it as a band. Alright, just to let you know. And the main topic, continuous spectra. Remember, continuous spectra contains all colors or wavelength. One example, sunlight is a good one. If your sunlight is split it to prism, you will see the rainbow color. This is one example of continuous spectra. So how do we generate? We'll discuss that here. How do you produce that? We need to understand a few things. So do remember that I have three things here. This is Kirchhoff's law of spectroscopy. So number one, you have a solid object produces light with continuous spectra. Kirchhoff coined it as term blackbody radiation. Okay, if you have this object can emit light here. Even human emit light. Human emit infrared light. Depending on temperature, you will release different types of light, to say. Second one, you have a hot low pressure gas produce a light with spectral lines. So this is emission, and the third one is absorption. Okay, but we shall concentrate on the continuous spectra. Okay, so remember that all objects emit radiation, because all object vibrates, and when it vibrates, it produces electromagnetic waves, which means the light. Alright, the higher the temperature, you can expect that the light produced would be more and more energetic. For example, this is example of blackbody spectrum. Blackbody is a object that release all the energy that it absorbed here. One example is that if you look at this here, these are the temperature of an object. So we start off with 3000 K, the value here. This value, you see the blackbody spectrum, and this object here, the size is very small. So you see that if you heat up an object up to 3000 K, you will see a red color of the object. Okay, and then let me take an example that is more relevant to us. Take the sun. The sun here, temperature is about 5500, and somewhere in the middle here. You see that all these, this is the light that the object will emit at that temperature. Okay, to make things simple, assume it's 6000. This is the light that majority of the light here. Say majority of light will emit this at that temperature. Let's say the sun 6000, you see that 6000 you emit all this visible light. That's why the sun, the color is white. Also, you have UV radiation coming from the sun. So the higher the temperature, you see that it's more energetic here. It will release even more powerful EM radiation. So I give you more example. So blackbody spectrum, this is some definition. Remember, in blackbody, there are things that we want to take note here. What happens if you increase the temperature? What happens to the blackbody? Two things will happen. Number one is that the blackbody curve will shift towards a higher frequency, or you can say we shift towards a shorter wavelength here, and the intensity will increase also. The area under the curve will increase as you increase the temperature. Please do remember that. So these are examples of continuous spectra produced by the temperature, due to the temperature of the object. and focus more on this. This is the temperature. Let's say you have temperature 2500. You'll see that why some stars they are reddish in color. It's because when you look at the black body temperature, black body spectrum here, majority of light here is actually giving you red. Alright, and there are some infrared radiation that we cannot see. So this is what we can see. It's reddish because you can see majority of light is red. Infrared we cannot see, so we ignore it. And as you increase the temperature of the object here, the continuous spectra produces of this shape. So this is about our sun. You see that majority of color here, when you overlap all this color, this is where you get your white light. But do remember we have a little bit of UV infrared that we cannot see. So this is color of the sun is actually white here. And lastly, why do you have some stars being bluish in color? It's white blue. Because when the temperature is very high for that star is 18,000 Kelvin, you see majority of color here. Majority of color produced is actually ultraviolet. Okay, with some violet bluish color being present, and this is a dominant color. That's why you can see it is bluish. Yeah, so this object, this star here at this temperature emit mostly ultraviolet radiation with some visible light of bluish purplish color that we can see. That's why it's bluish in nature. Alright, so remember that in continuous spectra you get it, and when you heat up the object, different temperature will give you a different black body spectrum. In general, the black body spectrum, the higher the temperature, the bigger is the curve, as well as the shorter is the peak wavelength. Okay, so this is one example of a spectrum that is due to a different temperature with a different light being emitted. So I think that's all that I can tell you about this continuous spectrum. Thank you.